Welcome! In this series, I've been covering the creation of a game engine called Midpoint. Midpoint will be known for its user experience, AI integrations, and open world focus. In this video, we will be covering the setup for the wgpu pipeline. This is necessary for displaying a blank scene, but also includes various unique touches which will be used, for example, in rendering models and landscapes. Now we begin by taking a look at the architecture, particularly that of the renderer. Inside, you can see we have files for utility grid, landscapes, models, shapes, and more. Only some of this is necessary for this video. If we jump into the core.rs file, we will find most of our setup code there for now. We begin with a rather large set of use statements, as this is a rather long file. Smaller, focused files are often preferred, but some functions are best not or even impossible to break down due to issues such as memory management. Technically, you could skip importing some of the local modules, such as grid and landscape, for now. Otherwise, feel free to jump ahead by checking out the GitHub repo. As we continue, define an invoke function so we can interface with the Tauri background process. We also need to set up some simple parameter structs which are passed to the invoke function when making various calls. The background process requires this data. Now, things get a bit more fun. Our vertex is the center of a lot of graphical computation, and as such is defined carefully and precisely. This data will be passed into our shader in exactly the same format as specified here. As you can see, the attributes on the buffer layout match those on the vertex struct. Now, let's define our camera. This is what we'll see into our scene. Due to the fact that we need to share this same camera between processes and initialize it only once, we go through some hoops here when defining it. Next, let's hop into the simple camera.rs file, where we can separate our camera logic. We will only be using NAlgebra here, which I handpicked as a highly capable and popular mathematics library. The camera has a number of obvious properties, among others which may be new to you. The important part is to understand how all the properties are used to compute the view projection matrix, which is passed to the shader to determine which vertices appear in the view. As we define the methods for the camera, it starts very simple with a basic new function. However, here you can see the update and rotate functions both update the view projection matrix. This means we can update properties such as position, call the update method, and therefore update the view projection matrix. Alright, let's get back to the core.rs file. We continue with the renderer state struct. This is what will define what is actually being rendered in our scene. As you can see, there are the assets near the top and wgpu objects near the bottom. Both are necessary for the creation and usage of the renderer state. Now we can start defining the methods. As with the camera, our new function is relatively straightforward. It assigns the wgpu objects, some empty vectors, and adds a utility grid. We won't be covering the grid in this video, but it is available on the GitHub. Now we have a few methods which will be used later. Feel free to ignore them for now. Okay, now we need to carefully define a cross-process boolean, which will help us to pause rendering in certain cases. This can be sometimes useful, for example, when importing a model into the scene. Like with the camera, we need to initialize and retrieve the renderer state in a thread-safe way. Great. Let's move on to the start render loop function. This will be called from U, so it will be a WASM bindgen function. First, we use the WebSys capabilities to get our canvas from the U component. Then we set up the wgpu instance, which will not require DirectX for now. Be careful here. Version mismatches can make this code very tricky. You also need to be sure to include the target architecture instruction. You might be surprised to see that we create a winit window inside of our WASM editor, but that is the best standard today. Ultimately, you will have a clean surface and all the complexity is hidden from the user. Now, we continue with some typical wgpu setup. We need an adapter, device, and queue to properly set up the rest of the pipeline. The default settings and features are perfectly acceptable for this stage of development. Here we configure the swap chain on the surface, so we can have a fully functioning swap chain. We also add the shader code. Inside the start render loop function, we will take advantage of our camera capabilities. We use the resulting view projection matrix to set the initial buffer data. For these bind groups layouts, we need to prepare uniform data. This data is visible to the vertex shader. These slots mentioned in the layout will hold buffers such as the view projection matrix we just set on the camera. We have one more bind group layout, which captures more data, presents it to the fragment shader. First, it collects an array of textures. Second, it accepts a sampler. Third, it accepts a uniform data, in this case just a 1 or a 0 to indicate whether to render color or texture data, both of which are stored on the vertex struct. Here we create the bind group for the camera, which we will use alongside other bind groups during frame rendering. We also create the two buffers for the render mode. The color instance is set to 0 and the texture instance is set to 1. Finally, we bring all of the bind group layouts together into a pipeline layout. Next comes some depth stencil work, which will be necessary for 3D occlusion, where some objects show in front of others. Simply create a wgpu texture with depth 24 plus format. Then create a texture view as usual. We also create a configuration struct related to the depth stencil. Now we will do the work of actually creating the pipeline. It's somewhat large, but also mostly standard for our simple setup. We use your convenient vertex method and pull in our shaders in swap chain format. The primitive configuration specifies the optimal way in which we supply our vertices and indices as a triangle list, while also specifying some other common options. With all of our wgpu objects created, we can easily instantiate the renderer state. Finally, we've reached the frame rendering functionality. This essentially uses the web-based request animation frame to render a new frame at the optimal time. Also pay attention to our use of the drop function on the state guard. This ensures that we can update the renderer state while rendering frames. Here's a small helper function which actually uses the request animation frame function. Inside the actual render frame function, we need the camera again. We also need to get a frame from the swap chain, which we will display after preparing the next frame. The encoder will just allow us to start the render pass. Now we prepare the next frame. We start by beginning the render pass, defining a clear color, and setting the depth stencil texture view from earlier. To pass our camera data along to our shader, we do it right here. This way the uniform buffer gets updated as the camera is moved around. Now, setup is essentially complete. However, here's how we will pass the grids, landscapes, or models data along to the shader. Notice how all the bind groups are bound and the indices type is U16. This is because we have a smaller number of indices on the grid. As you can see, landscapes have so many indices in early testing that the indices type had to be bumped up to U32. We also submit the next frame to the queue while calling the present function on the current frame. That's about it for our wgpu pipeline setup. This will give us the basis required to render wgpu in our editor. Later, we will render wgpu on native platforms outside of the editor. If you enjoyed this video or learned anything, please subscribe. Thank you.